Okay, good morning. Let's resume our discussion. So what were we discussing in the last class? Any of you brief? Give 1 or 2 points and what were we discussing in the last class? What is that we were discussing in the last class?
We were discussing about hard features based ensemble classification for face detection. And we saw the 4 basic steps, that is finding the hard features, then converting into integral image, applying the adder boost algorithm, and then cascading and finding the region of interest.
Right. So let's now in this class, let us get the another feature extraction procedure, widely well known and widely used feature extraction procedure. And this procedure, as I mentioned, referred to as scale invariant feature transform. And this has the provision not only to give a descriptor like HOZ, and it also has a provision to identify the key points or the feature points. This is referred to as scale invariant feature transform, proposed by David Lowy in 2004, and it is quite famous in computer vision. Before the advent of deep learning, almost SWIFT is the default procedure for feature extraction and as well as feature representation at a basic level. So let's see what this is. The previous discussion that we had, we discussed about Harris corner detector and Moravec operator, which are used for very good feature key point detection. That is, given an image, where do we look for the information? Because as I mentioned, there are 2 kinds of algorithms. One kind of algorithms takes the whole image and gives the features for the whole image and perform either template matching or classification. Other kind of algorithms will look at only some specific regions in the image, and whatever the task, let it be a detection or a recognition or a any other task, they perform based on the features and not using the whole image. So they are sparse methods or feature-based methods that rely on first finding key points. So this scale invariant feature transform has the same approach of finding key points. Like Harris corner detector and Moravec operator. In fact, this has been proposed in the similar lines as that of these methods. And the and this also has the provision to provide the key point description or the feature description. At key points. This also uses a similar approach like histogram of orientation gradients, but has a better feature in terms of normalizing the description of the key point or the feature description of the key point with respect to a particular orientation at the key point. So it finds out the description with a reference at each of the key point, and hence this is somewhat more invariant to rotation. Even though it uses HOZ, the features of HOZ used here are more they are invariant in terms of comparison or in terms of matching or establishing correspondences, because they are described with reference to a particular orientation, particular scale, and so on. The key aspect of this, as the name indicates, is scale invariant feature extraction. So this is slightly unlike the face detection approach, where hard features are used this feature extraction and key point identification, they are quite generic. Okay. Okay. So given this, let us see what are the steps in this scale invariant feature transform. So mainly, as I mentioned, it has the invariance across scales. Okay, and it also gives the orientation with reference to a particular orientation. It also has several steps by which it eliminates the false key points. Usually when we have seen in the earlier examples, there may be many false key points that appear. And you also have seen that Harris key point operator is anisotropic, in the sense that if there is a small rotation, the key points detected will be different from what we would have been detected with no orientation. No, this is not like that. So these are all the features of this, and this is proposed by David Lowy. Okay, in 2004. It has, as I mentioned, the highest cited paper in computer vision. Of course, now given the deep learning era, there may be some papers which are closely cited or even more cited than this paper. But before this deep learning developments, this is the highest cited paper in computer vision. Also, let's see some of the aspects of this. See, one main aspect is, say, in Harris corner detector, how do we, or in Moravec operator, when do we say that there is a corner point or a feature point? If there is an object like this, okay, how did we represent a interest point or a corner point? Any answer? Any quick answer? Say this is one interest point, second interest point, third interest point. Okay, so if there is a car, these are all the interest points. How do we characterize the interest points?
It will change in intensities in all directions. If there is significant change in intensities in all directions.
If there is a significant change in intensity distribution or intensity intensity profiles in all directions. So we have identified a region and we have moved in all directions, and then have seen either explicitly moved in Moravec operator or implicitly identified the direction in which the minimum change is there, and that change itself is greater than a threshold. That we have seen in the Harris corner detector. But the problem here is, see, in either of these things, we need to consider a window. And that window, whatever we see, okay, to move and find out the variation in the neighborhood is a discrete window. Okay, you need to take 3 cross 3 or 5 cross 5, whatever. And then you have to look at it. There is a nice signal processing approach which will give us the high value when the variation in the intensity distribution is high in all directions. Say if we convolve this image with a Gaussian mask or Gaussian filter. Okay, so assume that this is a one-dimensional Gaussian, whichever I have plotted here. I hope you all know the expression for Gaussian. Okay, so this Gaussian, this is one-dimensional Gaussian. You also know that the two-dimensional Gaussian can be represented in the similar fashion as one-dimensional Gaussian, but you can consider it as one-dimensional Gaussian like this, and then you just rotate the one-dimensional Gaussian, okay, to form a bell-shaped curve. Okay, that's a two-dimensional Gaussian. I hope you can easily understand or imagine that. So that will look like, say, the expression for it will be something like that. I'm just writing in a simpler form where the variance is covariance is 0. You people have seen this expression as well? Anytime, yes or no? Huh?
Yes, sir.
Yes. Where did you see?
Wireless communication.
Oh, very good. In wireless communication, they discussed about two-dimensional Gaussian distribution, is it?
Yes, sir.
Multivariate Gaussian distribution.
Yes, sir.
Right, good. It comes in several fields. It comes even in statistical signal processing. It comes in machine learning. It comes in almost many signal processing related fields. Okay, this is two-dimensional Gaussian. As you can see here, it has actually a variance in x direction, variance in y direction. If both are same, it will be sigma x square, sigma square, that's all. Okay. So otherwise you can also have the mean differently in x and y directions, and then variance also different. It can be sigma x, sigma y, or sigma 1, sigma 2. Okay, it's in the way you write. So this is two-dimensional Gaussian. We can write g of x comma y. Okay, and this is what we have written before is z of x only. Right? So hope this is clear. Now, this two-dimensional Gaussian, if I convolve with two-dimensional Gaussian an image, okay, if an image is convolved, if I let I be the image, okay, and then I just want to get a h, for example. So let's write h is equal to I convolved with g. Then what will happen in h? That means what gets highlighted in the convolved image. Convolved image I see. Okay, what gets highlighted compared to I? Can any of you tell? This procedure of convolution with a Gaussian kernel highlights what? A quick answer is welcome.
Intensity gradient.
Okay.
Low, high, low.
Can you repeat?
Low, high, low intensity gradient, sir.
Okay, will it highlight the low, high, low intensity gradients? Any other answer? What does it highlight? If I just convert
Corners.
huh?
Corners, because the intensity at the peak is highest.
Can you repeat? I am not able to hear.
So corners.
Corners. Okay, will it highlight corners?
Because the intensity at the peak is...
see if there is a fine, it of course it highlights if there is a small point. Okay, but it smooths out also, right? So for example, what happens if I put a two-dimensional Gaussian here? Okay, in this region, if I assume that I have put two-dimensional Gaussian in this region, what happens? It blurs the edges, or it also blurs the corners, because the average of this is taken and put at the center, right? So when I perform convolution task, okay. So what does it highlight then? If there is a single point here, okay, and then I apply a Gaussian around this, okay, will that highlight the corner point, or will it takes the neighborhood values and then puts it, smears it? Oh, it blurs it better. Okay, so what it highlights is, it highlights uniform regions. Or smooths out noise. Okay, if there is a strong edge or there is a strong corner, then it may just retain it still, but still it blurs it. Okay, because I perform it, it's a smoothing operation. So in signal processing terms, what kind of filter is this? If I consider this as this is in spatial domain. Okay, let's take with
averaging filter, sir.
Very good. So if I take this as spatial dimension, and if I just transform it to the frequency domain, okay, frequency domain representation of Gaussian is what? Frequency domain
Gaussian only.
Yeah, it's Gaussian only. Okay, frequency domain representation of a Gaussian is again a Gaussian. Okay, you can see that those, I think this also comes in communications. Of course, also in some other context in signal processing itself. So this will be G of omega, G hat omega you can write. Okay, and this is also a Gaussian. So frequency, this is a Fourier transform. These two are Fourier transform pairs. Okay, so frequency domain representation of Gaussian is also Gaussian. Only the difference is if it is wider here in the one domain, it becomes narrower in the other domain. Okay, if it becomes wider here, this becomes narrower in this domain. Okay, that's only the difference. Because it's narrower in spatial domain means what? It is quickly changing in the spatial domain. Okay, and hence in the frequency domain, it will quickly changing means what? It has a lot like high frequency content as well. That's why in frequency domain, it will be flat, indicating that it has low frequencies and then high frequencies as well. Okay, so hope those many of the signal processing students are here. Hope you all can relate it. No, so this extract and hence this extract now usually Gaussian is a centered at the peak, and hence this is a kind of Gaussian here. And it is a what kind of filter if this is like this in frequency domain? What kind of filter do you attribute this to?
Low pass filter.
Yeah, it's a low pass filter. It acts as a low pass filter. What does it mean? It only highlights the low frequencies or not changes. Okay, sudden changes is being attenuated. Okay, that's why we have written that it is smoothing filter. Okay, smooths out noise. Okay, now let's come to the first derivative of Gaussian. Okay, let me sketch little clearly so that you appreciate or you understand what happens. Okay, assume that this is a Gaussian. Now, if I ask you to sketch the first derivative of Gaussian, let's do it for one dimension. Same thing happens in two dimensions. Just as I said, it will be like, so if you just take a paper and then rotate like this, okay, whatever you get. With a circle, how do you make a sphere? Same thing happens even here. Okay, so now why we would like to get the first derivative of Gaussian. D by dx. Okay, or dou by dou x also you can consider. See, in two dimensions, all the partial derivatives and all come into the picture. So it's a little slightly involved compared to this, but similar. Okay, what will happen now if I take in derivative of this? Can somebody guess what will happen? I think this is an important thing to understand. What will happen? See,
It crosses the 0
yeah, it will start with
at peak value.
see Gaussian. If you see, it is very smooth. If you see at infinity and minus infinity, so very smooth means what? You need to see derivative from the graph itself. So it will be 0. Okay, almost 0. And then is it slope increasing or decreasing in this region? So let's see in each of the region, what derivative is nothing but the slope. Okay, the interpretation of derivative is slope. That's all. Slope of curve. Okay. And hence, what is the slope now? Is it increasing or decreasing? It keep increasing for some time. Okay. It's 0 almost and then keep increasing for some time. After some time, what happens now? After here. Okay, is slope increasing or decreasing? Compared to here, this is increasing now. After here, is slope increasing or decreasing? From here. Any comment? And what is slope here?
0.
0. Okay, so it has to come down first. So what will happen? It keeps increasing for some time and then goes to 0, right? It goes to 0. After going to 0, what happens to slope now? Is it increasing or decreasing or in which direction and so on?
Decreasing.
Decreasing in which direction? Decreasing in the sense, in fact, it is increasing in negative direction or decreasing. Okay, from here. So it goes like this and then goes to 0. So it will be something like that, close to that. Is this clear? This is how the first derivative will be. Okay, let me just sketch better. But essentially, this is the curve. Right? This how is the first derivative of Gaussian is. Okay, exactly here it will hit 0. Okay, these two are same. Okay, now this is the first derivative. Fine, it both will be symmetric as well. So this we write dou z by dou x. Okay, this is the d of x derivative, like differentiation of Gaussian. Okay, for timing. Now if I perform one more derivative. Okay, what do you think will happen? I want to write the second derivative. Now, this first derivative, okay, difference of this Gaussian, what does it highlight? It is what kind of filter if we consider, say in frequency domain, if you see this also becomes a band pass filter. Okay, it's the low pass filter and this becomes a band pass filter. Two Gaussians, right? So it's a kind of band pass filter. So it extracts a particular band of frequencies, not low or not high. Okay, so now let's sketch the second derivative of Gaussian. What do you think will happen? Here the slope is 0 almost. It is increasing and then decreasing. So can somebody comment how will it be? No idea? Slope will be 0 and then increasing and then 0 here. Right, exactly here it will be 0. Okay, it should hit 0 here, and then here slope is maximum. Okay, and then again 0 here, and then increases, and then like this. Okay, so this is referred to as inverted Mexican hat. Okay, you can see this. This is not triangle shape. This is again a looks smooth curve. This is the second derivative of Gaussian, dou square g by dou x square. So now tell me, so if I convolve with this anyways, okay, this is second derivative of Gaussian. This is also referred to as Laplacian of Gaussian. Okay, so if I okay, this is also referred to as Laplacian of Gaussian. If I convolve with this, okay, Laplacian of Gaussian, anyways, I write just L of G, L of L. Okay, I convolve with Laplacian of Gaussian, R I L. What do you think will gets highlighted? Which ones do you think gets highlighted? Any comment on this? Say if
Edges, sir.
okay, edges, do you think they gets highlighted? Yeah. See, edges, why do you think edges gets highlighted? See, it's a kind of, see, if you see, imagine in 2 dimensions. Okay, it's like, it has a dip at the center. Okay, in 2 dimensions, if you see, Laplacian of Gaussian, if you see, okay, del square G, how will it look like? In this region, it will have different intensities. Okay, and then in this different intensities. Okay, in this region, it may be say negative, right? Here it is all black. Okay, and then here it is all again, this is a different color. Okay, so this may be, this is another direction. This is all positive. One direction is positive. This one is negative and that is positive. Okay, this is negative. Right? So this is like this. So what do you think it will highlight? And 0 others outside. So how is it looking visually? So let us also sketch it in a inverted manner to see the other aspect as well. So if I just sketch this, what I'm doing is I am just negative sign of this is what I'm plotting here. That's all. Okay. So how does it look like now? This is in one dimension, what we have plotted, but in 2 dimensions, you can anyway imagine. How does it look like? This itself looks like a blob, or it say if there is a dip in terms of suddenly if there is a high intensity all through, okay, and then there is a corner here in between, okay, that's how it looks like, is it not? Or suddenly there is a intensity change at some point, okay, from the neighborhood. These are all different intensities. Then suddenly you have an intensity change here. These are all different intensities, and then suddenly there is an intensity change here. So that's what it easily can identify. So it is referred to as blob detector. So wherever the blobs are there, so for example, if there is a red blood cell or a white blood cell, if you would like to highlight the white blood cell or red blood cell, you can use with respect, if you convolve with respect to this, what happens if there is a sudden blob kind of thing, okay, compared to the neighborhood, that gets highlighted because the filter looks like that, right? And the greatness of this is, see, how do I control how much blob do I can recognize? Say in an image, for example, okay, say assume that there is a white blood cells and both red blood cells. Okay, red blood cells are very small, and then white blood cells we just sketch with this one, okay, are bigger. Okay, this is white blood cell, and then this is red blood cell. Okay, and there are several of such things. Several red blood cells, and then white blood cells of different size. Okay, now the question is, I can use the blob detector like this. Okay, I want to highlight both first red blood cells alone. Okay, and then I want to highlight the white blood cells alone later. Do you suggest me any procedure for doing it? What I have in my hand is a del square G. Okay, a Laplacian of Gaussian operator and an image I. What do you suggest?
Should be convolved with image to find red blood cells, and we have to increase the width of the main lobe for finding WBC.
Right, that's all. Okay, you take actually one sigma. So sigma 1, which is small. Okay, and sigma 2 is big, large. Okay, if you convolve with sigma 1, what we get is, so I convolved with Laplacian of Gaussian with sigma 1. Okay, will give us RBCs. Okay, or highlight RBCs. I convolved with Laplacian of Gaussian of sigma 2 will give us WBCs. Okay, so this has the flexibility to extract features at different scales, or the blobs at different scales, or even the corners at different scales. That is the beauty of this. The earlier methods doesn't scale up very easily, or to see the image at different scales or different resolutions. But this Laplacian of Gaussian, okay, will help us to extract the blobs or the corners at different scales. Okay, and that's what can be done through Laplacian of Gaussian. How do we do? Simply we add a parameter sigma, and this sigma will control what is the size of the blob I am extracting. Okay, if you convolve with a bigger Gaussian, like a larger sigma, which is a wider Gaussian, and Laplacian of wider Gaussian, then you will get actually a bigger blob extracted or highlighted. If you convolve with a narrower Gaussian, a smaller blob gets highlighted. That's all. Okay. So this principle is being looked at by David Lowy. Of course, even by the earlier researchers. But what Professor Lowy has done is relating this or computing this blob detector in a very effective and efficient manner. Okay, with the use of few other things. See, now we have come to the conclusion that if you are to extract good features, you take different sigmas of the Laplacian of Gaussian, okay, and then convolve with image, you will get a good features. Okay, so but the problem here is Laplacian of Gaussian itself is very costly to do, in sense that you have to extract in 2 dimensions. If I write dou square g by dou x square, okay, plus dou square g by dou y square. This is what operation I have to do on g, which is defined x comma y. Okay, so if I consider gx comma y as we defined before, okay, so now in this, what we, if you would like to compute the Laplacian of Gaussian, what we need to do is we need to find dou square g by dou x square and dou square g by dou y square. Okay, this computation, each of them takes reasonable time and effort. Okay, and it's not very easy. And what we are suggesting, we need to first compute Laplacian of Gaussian. We have a big expression, and that we need to convolve with images. So that takes a computational effect to computational effect. So what David Lowy has come up with is a simple solution to perform this. That is using difference of Gaussians. See, please make a note here, since we are saying that this sigma is also important. Let us represent from now on gxy comma sigma, and then let us write this as, even let's not bother about the variances in x and y are also same. Let's assume that, and simply we have x minus mu x. In fact, if we means are also 0, we will have a simple Gaussian expression x square plus y square by sigma square. That's all. Okay. Here variance in x and y are same. Okay, and covariances are 0, and then the means are also 0. So for this, we can anyway compute the Laplacian Gaussian. If you compute and see, there is a good terms. Okay, x square multiply, like in addition to the Gaussian term, there is a term that with x square and so on, which gets multiplied to this. Okay, and it is not very simple to implement, and then perform convolution, all those things. So what there is a relation in the previous researchers that this Laplacian of Gaussian can be related to difference of Gaussian. Okay, how is it related? This is the difference of Gaussian. So sigma times this is equal to this, and difference of Gaussian you can discretize and write simply. What is difference of Gaussian? This difference of Gaussian, now we are discretizing with taking the Gaussians at 2 different sigmas, which is one is k sigma, another is sigma. Okay, so this is purely difference of numerator. If you see, is purely difference of Gaussian. Okay, and the denominator anyway, as you can see. And here you have actually the Laplacian of Gaussian. So effectively, through this, what we can do is difference of Gaussian is a good approximation to scale normalized Laplacian of Gaussian. The other advantage we get here is, see the sigma square, when you perform Laplacian of Gaussian as well, you will have the sigma square term in the denominator. Now you are multiplying with this. So it is in some sense is referred to as scale normalization. That's happening. Okay, scale here is being represented by the variance sigma. And through this, what we can do is, you need not compute the Laplacian of Gaussian. Even if you would like to perform blob detection, still we can have the difference of Gaussian, which can also be used effectively Okay, with some scale normalization to find out the blobs are the corner points, key points. Okay, so essentially we can represent this as capital X being all these things taken together. Okay, and then sigma square. Okay. So this is one of the good finding or breakthrough from the David Lowy. Representing a Gaussian, Laplacian Gaussian through difference of Gaussian. See, even difference of Gaussian, he has not explicitly computed, but he has explicitly computed, but there is a nice way in which it is computed. See, if we consider an image, what happens? First, let us take a image. Let's convolve with a particular filter. So this is actually assume that this image convolved with a Gaussian of a particular sigma. Okay. Now, if I want to construct the difference of Gaussian, the idea, as I mentioned in scale invariant feature transform, is look at the features, corners, which are stable across different scales, not just at one scale. So what do we, which is the one which defines the scale here? So one, if you see, even the, say if I have an image, if I want to extract, if I want to see the information at different scales, just by through a convolution with a Gaussian, do you have any suggestion? Assume that I have a Gaussian function only with me. I want to see the details of the image at different scales. Okay. Well, any suggestion on how do I do that? Say, assume that as we just mentioned, we have actually some small objects and bigger objects and so on. Even if when we considered the previous example, we wanted to see the objects at different scales. Okay, small scale you can consider here are small size and big size. So if we have an Laplacian of Gaussian, what did we suggest? For small size, convolve with the small Gaussian with an arrow sigma or small sigma, and corresponding Laplacian of Gaussian with small sigma, corresponding Laplacian of Gaussian with bigger sigma. Similarly, here also, if the details, if I convolve with a Gaussian of larger sigma, what happens? It looks at a bigger region. So a sigma 1, which is, say for example, if it is sigma 2, if it is bigger, it looks at a bigger region. If sigma 1 is smaller, it looks at a smaller region. Right? So if I want to look at the information in the image through a Gaussian, what I need to vary at different scales, what I need to vary is just the sigma. So this gives an idea of visualizing the information or extracting the information at different scales. Or this determines the scale at which information is extracted. Okay, so now if I want to form a scale space, the reason for forming scale space is I want to see the information not just at one scale, but also would like to see it in different scales. And then I would like to extract key points which are stable across different scales. Okay, so for that, what we wish to form is a scale space. Okay, so what do we mean by forming a scale space? I start with this. Then what I will do, I will increase the sigma with which I look at. So initially I may start looking at a smaller sigma. Say I have an image I convolve with sigma naught, and then sigma 1, sigma 2, okay, and sigma 3 and so on. Sigma 1 may be k times sigma naught. Okay, that is slightly higher. Assume that if k is greater than 1, okay, or k equal to root 2 more specifically, Okay, then what will happen? Sigma 1 will be higher than sigma naught. And then this is equal to k times sigma 1 or k square times sigma naught. Okay, this is equal to k cube times sigma naught. So through this, if I have, this is the original image. And what is this image? This image, whatever I have, I am writing here, this is actually the same resolution, but the information details are looked at as with a narrow, convolved with a narrow Gaussian. Okay, so small details are more highlighted. The details that are spread across are not very much focused. So this is I convolved with G sigma naught. Okay, and then this is the I convolved with what? I convolved with G2 sigma naught or G sigma 1. Similarly, I can perform I convolved with G sigma 2 and I convolved with each of these looks at the same image information but at different scales. Now, if I want to formulate a difference of Gaussian, these are all the Gaussian convolved images. Now we would like to bring in difference of Gaussian images. Why we need difference of Gaussian images? For feature extraction. How do I bring in? Say just simply I perform minus operation between these two. Okay, and get an image. Difference of Gaussian image. And this is what? Say I can consider I convolved with difference of Gaussian image at sigma naught. Okay, if I consider sigma naught as the reference, or I can consider sigma 1 as the reference or sigma naught as the reference. So we are considering here k sigma minus sigma. Okay, so this, if we consider sigma, we represent with the smaller one. And this again, I perform difference. So once I construct a scale space through convolution with Gaussian, different sigma based convolution with Gaussian of different sigmas. Okay, so now I can construct the difference of Gaussian space at different scale space. Hope you people understand. Now, in this difference of Gaussian, what we want to see is, we want to see the key points which are stable across different scales. Okay, so that means, say for example, as I mentioned, the Laplacian of Gaussian can be easily approximated by a difference of Gaussian. We can perform scale normalization dividing by sigma square, corresponding sigma square, to bring it Laplacian of Gaussian itself here. After performing that, what we see is in this, okay, say if there is a across this, say if there is a key point here, okay, key point means the value higher than a threshold. Okay, that itself is a feature point. So does the same key point exist even in this scale or not? Does the same key point exist even at this scale or not? Okay, there are some key points which may exist only at this key point, at this scale, may not exist here. Okay, and then may not exist here. So this key point, whichever point 1, is stable across scales. These key points are not stable across scales. Okay, these blue points are not stable. And hence these are not considered as good key points. This is considered as a good key point. Okay, so what they do is they form now a scale space with 3x3 window here, same location 3x3 window here, and then same location 3x3 window here. So the total number of pixels are how much? 3 cross 3 cross 3, which is 27. Okay, if the center pixel, whichever is there, center in scale space, which is center in scale space, this is the one. Okay, center in scale space is highest in all 27 pixels. It is a key point. That's how they define. So it has to be there in across different scales, but it has to be higher. Okay, in the scale where I see. Otherwise, it say it can be attributed to this scale, or it can be attributed to this scale. So the any point, key point that is highest across the different scales is considered as the stable or a valid key point. Okay, this is how the key point is localized. In scale invariant feature transform. Okay. So previously, as you have seen, corner points, how did we localize? By using the R measure. Okay, in Harris. Here it is first localized by this. So if we localize by this, you may get many key points. Of course, if this also is a key point which is not there even in other scales, you still may get a consider it as a key point. Okay, at the beginning. Okay, then we will throw the key points which are not very potential in subsequent steps. And this is done at one resolution now. So to bring in further what we do, say we need to convolve with sigma 4, which is k power 4 sigma naught. See, if we keep convolving like this, the variance of the Gaussian will become much higher. So then what the alternative for this is, instead of looking at the details, say if this is at 100 cross 100, instead of looking at the details at 100 cross 100, if I downsample this, okay, if I downsample this, that is downsample by 2, and then this becomes 50 cross 50. If I convolve with the same sigma naught, okay, Gaussian with same sigma naught, what do you think will happen? It is equivalent to convolving that at the higher resolution with, okay, 4 times our sigma naught. Is it not? It is equivalent to some 2 times at least. Okay, 2 times sigma naught. Because what happens? See, this sigma naught here in this resolution is equal to convolving this with 2 times sigma naught there. Why am I saying that? Because the information, whatever I see here, this now has become a like half in both directions. Okay, so sigma naught by 2, sigma naught by 2 in roughly if you consider, okay, then it is like that. So if, because sigma square is what we see, then probably you can consider 2 sigma naught there. Okay, so what essentially I am trying to convey is, if you convolve with the same sigma at the higher resolution and lower resolution, the information extracted is not same. It is a small sigma naught here will effectively have a higher sigma. Okay, the region you look at by convolving with small sigma naught here will be much higher, okay, in the higher resolution. So if you would like to reduce here in this side, that is to, if you would like to look at a smaller region, better not bring in the sigma naught even smaller. What we can do is alternatively, we can downsample it and then convolve. Or even this side, if you would like to go for further high region to be looked at, okay, with a convolution with a better sigma or a larger sigma, okay, you can equivalently do that by bringing this, like the whole image downsampled by 2 and convolving with a smaller sigma itself. Okay, so by that what we can do is we can keep the scale space of the Gaussian, that is sigma naught to sigma 3 constant. Okay, if you would like to go for sigma 4, no need to go for sigma 4, just simply downsample it. Okay, and then you start from directly from k square sigma naught, that is from sigma 2. Okay, So you have gone one step back, but because you have downsampled, you are one step ahead. Okay, it is equivalent to this k power 4 sigma. Okay, this is equivalent to sigma 4, which is equal to k square times the sigma 2. Instead of doing k square times the sigma 2 convolution in this higher resolution, we can equivalently do sigma 2 based convolution in the lower resolution. Okay, that's what I am trying to convey. So the next scales, how they form further scale spaces to bring in the downsampled resolution, okay, and then start convolving this with k square sigma naught, k cube sigma naught, okay, and then k power 4 sigma naught, okay, and then probably k power 5 sigma naught, okay, and then again from this get the difference of Gaussian. Further step down is you go even to the smaller resolution. Again here you start directly k power 4 sigma naught. Okay, you have come from here. Okay, this has come here, and then you just proceed. Okay, k power 5 sigma naught and so on. So like that, what happens is we are analyzing the image at different resolutions. In each resolution, we are looking at different scale space. So the details at several scales are looked at essentially, and the features which are elegant across scales are decided, not just at one scale. Okay, so this is what is being done for key point localization. After this key point localization step, as I mentioned, there are two steps for eliminating the key points which are at the edges, because Laplacian of Gaussian also extracts key points at the edges. Okay, so there are two steps to eliminate the key points.
Sir, we have a class now.
You have class, right? Yeah, to eliminate outliers and other edge key points. And there are other steps to finally get the descriptor as well. We will discuss in the next class. If there are any questions, you can ask. Otherwise, we can leave now. Thank you.